In this video, we're going to talk about a different type of exponential model, exponential growth and decay models. So many natural phenomena tend to follow an exponential growth or decay, and both of these can be described using the same basic formula, so A equals P e to the RT, but we're going to do some new notation that's common for these type of problems. So first of all, if you have uninhibited population growth, so that's where there's nothing preventing the population from getting bigger and bigger. So this is an exponential law. Then the population can be modeled using this formula. So n of t is the population after t time has passed. Okay, so it doesn't have to be in years, but it often is. But it depends how it's defined. So that's the population after t amount of time. Okay, n0 here, or n naught, sometimes they say, is the initial population, so at the beginning of the model. And k is called the growth rate, and because the population's growing, it's going to be a positive constant. Okay, sometimes p, letters p for population is used instead of n, so just be aware of that. Doesn't really matter if you use an n or p, but usually they're the same. Okay, but this number here, so this is not n of 0. Well, I guess it actually is n of 0, but they call it n0. So it's the population at time t equals 0. So let's just do an example to try and get used to this. So suppose a colony of cells follows the exponential growth model. N of t is 200 times e to the 0.12 times t, where t is in days since the colony began. Okay, so n of t is the total number of cells after t days. Okay, so this should be after t days, because t is in days. So if we wanted the initial number of cells, that's going to be n of 0. Okay, so initial number, that means that t is equal to 0, so after 0 days. So that's going to be 200 e to the 0.12 times 0. So that's 200 e to the 0, and anything to the power 0 is a 1, so that's 200. Okay, so that's why this number here in front of the e is always the initial population, because when you plug in t equals 0, the e part goes away. So that's 200. So we didn't actually have to do any work there. You could have just known it was 200. How many would we have after 18 hours? Okay, so now you want to be careful. 18 hours, but t is in days. Okay, so that means that this t is less than 1. Okay, it's less than 1 day. So it's actually t equals 18 over 24, because there's 24 hours in a day. Okay, which is actually 3 over 4. So what we're looking for here is n of 3 over 4. So that's 200 times e to the 0.12 times 3 over 4, which is going to be approximately 218.83. Okay, so that's approximately, so almost 219-ish cells. Okay, what if we want to know how long it takes for the colony to reach 700? So for this one, we want t so that the population number, n of t, is equal to 700. Okay, so that means that we're going to have 700 is equal to 200 e to the 0.12 t, and we want to solve for t. So we're going to divide both sides by 200 because we want to get the e by itself. So 700 over 200 is just 7 over 2, and that's e to the 0.12 t. Now if we do the switch or take the ln of both sides, whatever you prefer, that's going to be 0.12 t is equal to ln of 7 over 2, which means that t is going to be ln of 7 over 2 divided by 0.12, which if you compute is approximately 10.44. So that means it will take approximately 10.5 days to reach 700 cells. Okay, so that's the idea there. Now I'm going to leave example 2 for you to try. And let's talk about uninhibited radioactive decay. Okay, so here you might have some amount of radioactive material present at time t, and because of the uninhibited decay nature, it's also modeled by a similar equation. So A of t equals A0 e to the kt. Now here A of t is the amount of material, radioactive material, still present after time t. A0, again, is the initial amount of radioactive material, and K is the rate of decay. So it's going to be, because it's decreasing, it's actually going to be a negative constant. Okay, so here K is negative. Now they often talk about the half-life of for radioactive decay. So the half-life is the time required for half of the radioactive substance to remain, or to decay. It doesn't really matter which way you say it. Okay, so i.e. it's T so that A of T is equal to 1/2 times the initial amount. So half of it is gone. So for radioactive decay problems, the half-life, or it might be another point, so maybe some measurement that you've taken, can be used to find the K value. But you want to be careful. The K values are not usually nice numbers, and you want to try and avoid rounding them, because even small rounding makes a big difference. Okay, so let's do an example. So suppose a radioactive isotope has a half-life of 400 years. So maybe let's just highlight that. So that's our first piece of information. So what that tells us is half of A0 is, I wrote this wrong. So T, so that A of T is 1/2 the initial amount, okay, is going to be T equals 400. Okay, so that's what this thing tells us. Okay, now if 20 grams of the isotope are in a sample, how much was in the sample 500 years ago? Okay, so what they've given us is, so let me just highlight that as well. So 20 grams are in the sample 500 years now. So now, okay, so what that's giving us is A of 500 is equal to 20. Okay, so that's what that piece of information tells us. And what we want is A0. So we want to know how much is in there initially. So we're going to try to use this information to figure out K and then the A0. So the half-life, so we know A of 400 is equal to 1/2 times our initial amount. So what that means is 1/2 our initial amount is equal to our initial amount e to the k times 400. Okay, now if we divide both sides by A0, it's going to go away. So that tells me that 1/2 is e to the 400k. So now you can either take the ln of both sides or do the swap here with the relationship. So the exponent, 400k, is equal to ln, which is log base e, of the other side, which is 1/2. So that means that our k is ln of 1/2 divided by 400. Okay, now if you did compute this, so the number, what it looks like is negative 0.001733. Okay, but we're actually going to use this number here. Okay, so now we want to use our other piece of information to find A0. Okay, so now we also know A of 500 is equal to 20. So that means that 20 is equal to A0 times E. Now I know the K value is ln of 1/2 over 400, and my T value is 500. Okay, so now I can solve for A0. So I just have to divide by this E. So A0 is actually 20 divided by E, and then these zeros can cancel out to make it a bit easier. So it's going to be E to the 5 ln of 1/2 divided by 4. Okay, now if you compute this, you get 47.568. Okay, and then our amount was in grams. So the initial amount, is approximately 47.568 grams. Okay, so that's, so basically we use the half-life to find the K value because the half-life depends on the initial amount. That means we don't actually need to know the initial amount. Okay, so that takes out that variable, and then so we only have the K variable left, so we can solve for the K variable. Once we have the K variable, now the only variable we have left is the initial amount, which is the thing that we want. So we use the other piece of information that they gave us to find that. Okay, now I'm going to leave example 4 for you to try. So it's similar. And let's talk about exponential growth decay models that don't have unlimited growth or decay. So here, and it makes more sense that there's often some sort of maximum capacity for like a population. So if a population of, say, deer is in an area, once it gets overpopulated, the growth rate might slow down because they're running out of food, or there's nowhere to live. So once you often talk about some maximum capacity for these growth models. So when you have something like that, the model actually becomes a logistic model. So here, if we have some sort of carrying capacity, then the population after time t, the formula looks like this. So P of t is C divided by 1 plus A e to the minus bt. Okay, now here, C is the carrying capacity, so it's going to be a positive constant. And then our B is a rate of growth if it's positive, and it's decay if it's negative. So this negative here is in addition. Okay, so if you have a negative down here, that actually means that you're growing because it means your B is positive. Okay, so what these look like, so I'm going to try and draw this. Okay, so if we had a B that is positive, what's going to happen is we have the carrying capacity is some amount, and then there's some initial population. Okay, so let's say it's 0 and P of 0. And what it's going to look like is it's going to grow quickly. Okay, now at some point here, it starts to slow down, and then it approaches the carrying capacity. So this point here we call the inflection point, because the graph sort of changes shape. So on the first part, it looks like if we dumped water, it would hold the water. But on the second part, it's shifted so that if I dumped water on it, it would roll off. Okay, so that's the inflection point. Now where this happens is actually C over 2, the y value, or maybe I should write it as 1/2 C. Okay, so about halfway up, that's where this inflection point happens, and that's where B is positive. Okay, now if B is negative, that means that your population is decaying. So you still have this carrying capacity. Okay, so you have to be below it. Okay, but your population is decaying, and then it's going to, so this is B less than 0. So what it's going to do is it's going to decay and approach 0. So this is the line y equals 0. So it's going to look similar. So it decays sort of quickly at the beginning, and then at about halfway it slows down and approaches that asymptote. And then again, okay, this happens when you reach half the population size. Technically, these things continue, okay, like this, but it doesn't make sense to have, so the x-axis is like, I guess it's the t-axis, I should say, it's time. So it doesn't make sense to talk about negative time, so that's why I sort of stopped them, but the graphs do sort of continue like that. And actually I should have drawn this one a bit differently. So it kind of is like that. A little bit steeper at the beginning than what I drew. And so again, this point here is called the inflection point because the graph changes significantly there. So we call it concavity. It changes concavity. Okay, so that's what they look like. So let's do an example of this. Okay, so we're using data from a source, which is given at the bottom here in the footnote. We have a logistic growth model constructed to illustrate proportion of Americans that support decriminalizing marijuana. So if T is the number of years since 1980, so that means 1980 is T equals 0. P of T is a proportion of Americans that support decriminalization. Then this is the formula to compute that proportion. Okay, now it's in the right form for the form that was given. So the carrying capacity here is 1. But what I don't think this is worded that well. So what they're asking is, why can P of T not be larger than 1? Okay, so essentially, why is the carrying capacity 1 here? So first of all, P of T is a proportion. So it's like a percentage, but it's going to be computed as a decimal. Okay, so you can't have more than 100% of your population supporting decriminalization. That doesn't make sense. Okay, so that means because it's a proportion, it's computed as a decimal, it should be between 0 and 1. Okay, so that is one thing, because 0 is like 0% and 1 is like 100%. Okay, now another way to see this we can think about the parts, so not in the context, but just in the math. Okay, so if I look at 6.05 e to the minus 0.058 t, is this number going to be positive or negative? Well, we know that exponentials are always positive, so this number should be positive, times by a positive, so this has to be a positive number. Okay, so what that means is that the bottom, so if I add 1 to this number, then it should be bigger than 1. So all I did was add 1 to both sides, essentially. So the bottom's bigger than 1. So that means that the top equals 1, and the bottom is bigger than 1. So if I divide 1 by something that's bigger than it, I'm going to get something less than 1. Okay, so that means that P of t needs to be less than 1. Okay, so that's not thinking about the context, but just interpreting the equation. So let's think about part B here. Let's find the fraction of Americans that are expected to support decriminalization in 2020. So that's this year, actually. Okay, so 2020, first we want to figure out the t value. So how many years past 1980 is it? So 1980, 1980 plus 40 is equal to 2020. So that means that my t value is 40. So here we want to find P of 40. So I just plug in 40. So it's going to be e to the negative 0.058 times 40. So that is 0.627, which is going to be 62.7% of Americans. Okay, so in what year is it expected that over 90% of Americans will support decriminalization? So for that, we want how many years will it take? So we want t, so that the amount that support in that year, P of t, is bigger than 0.9, which is 90%. Okay, so that means we want to solve 1 over 1 plus 6.05 e to the negative 0.058 t is bigger than 0.9. So I'm going to multiply both sides by the bottom. Remember, I know the bottom is positive, so I can do that. So I'm going to have 1 is bigger than 0.9 times 1 plus 6.05 e to the negative 0.058 t. And maybe I should just write here. So the thing that I multiplied by, so it's actually bigger than 1, okay? But the only thing I care about really here is that it's a positive number. So I don't have to worry about switching the inequality. Okay, now expanding the 0.9 in gives me 1 is bigger than 0.9 plus 5.445 e to the negative 0.058 t. So now I'm going to subtract 0.9 on both sides. So I have 0.1 on this side is bigger than 5.445 e to the negative 0.058 t. Divide both sides by 5.445, which is again positive. And I don't want to round, so I'm just going to leave it. Okay. So ln is an increasing function, so I can take the ln of both sides and it won't affect the inequality. I'm running out of space here. So that's going to be ln of 0.1 over 5.445 is bigger than ln of this side, which is just going to be negative 0.058t. And then I have to divide by the negative 0.058. So here I actually have to flip the sign because I divided by a negative. Okay, so I get t is bigger than this number. And if you compute that number, it's approximately 68.92 years. Okay, so t needs to be bigger than 68.92 years, so about 69 years, which means that it's going to happen in 1980 plus 69, which is going to be 2049. Okay, so in the year 2049, more than 90% should support decriminalization. I missed the end there. That was a lot of work to find that, but that's what you'd want to do. So I'm going to leave example 6 for you to try. So it's similar, maybe, yeah, very similar to what we just did. So those are some examples for exponential growth and decay with no restrictions, and then with a carrying capacity on the population.